The last class we were looking at a very simple problem. We were trying to do this problem by using finite element analysis. We had done the preliminary work, which we will summarize later in this class, but let us pick the threads from where we left. We were here, we had defined the complete matrix, which we called a stiffness matrix, for this problem. In other words, we defined the matrices for the elements and then assembled them, and we got to this stage and applied the boundary conditions. It is quite clear from this stage as to how this problem can be solved. It is simple that these two matrix gives a set of simultaneous equations, in fact two equations, simple simultaneous equations, which can be written as say k1 plus k2 into u2 minus k2 into u3 is equal to 0, and what is the next equation? Minus k2 into u2 plus k2 into u3 is equal to p. There are two unknowns, u2 and u3. It's quite straightforward to solve them. So the first equation gives rise to a simple equation, an explicit in an explicit form, by defining u2 is equal to k2 divided by k1 plus k2 into u3. Now, what we have to do is simple. We have to substitute this value for u2 in the second equation and then write it down as minus k2 into k2 by k1 plus k2 into u3 plus k2 into u3 is equal to p. Is that clear? Now, once this is done, I have to just sort out or determine what is u3. Now, solving it, which is very straightforward, I can write u3 to be equal to p divided by k1 plus p divided by k2. P divided by k1 plus p divided by k2. Okay? And u2 can be written as p divided by k1. Is it clear? So we have determined or we have found out what are the displacements for this system. Once I know the displacement, what is my next step? I have to determine the strains, because ultimately I am interested in stress. So what we do is we solve these equations, determine displacement. Then we go to strain through what are called as strain displacement relationship. And then ultimately we determine stress through stress strain relation. Is that clear? So we first determine strain through strain displacement relationship. So what would be the strain? There are two strains, epsilon 1 and we can say epsilon 1 and epsilon 2, okay, as the strains that exist in the two bars, okay. And in this particular case, we can use the simple formula of change in length by original length. So I can determine epsilon 1. What is epsilon 1 in this case? Look at this. Remember that we had called this as node 1, node 2 and node 3. So what is strain in 1? It is nothing but u2 divided by L1, right? So from this relationship I can define the strain in 1 as U2 divided by L1. Is that clear? So, I can also determine epsilon 2, and epsilon 2 is written as, now there are two nodes here. So, U3 minus U2 divided by L2. Very good. So, once I know this, I determine the stress by a simple relationship. Again, for this problem, we have to expand these relationships later. Okay, for this problem, as sigma 1 is equal to E1 epsilon 1 and sigma 2 is equal to E2 epsilon 2, right, which on simplifying by substituting the values for U2 or U3, okay, from whatever we have derived here in this case, and substituting for K1 and K2, they are very straightforward substitutions. Okay. This is the relationship for U2 and this is the relationship for U1. Okay. Let me just do only one of the two, the other I can just write down, it is quite straightforward, okay, so that we do not waste much time on it. Remember what is K1 and what is K2, right? What are the K1 is equal to A1 E1 by L1 and K2 is equal to A2 E2 by L2. By doing that, it is very easy to show that sigma 1 is equal to P by A1, and you can just substitute it and see is equal to P by A2. Is that clear? So, you can straight away substitute it and you can see that, for example, if you have a doubt, I can say that we can work it out for this, okay, how we got it. Though it is very straightforward, it is useful to look at that quite closely. So, remember that epsilon 1 is equal to, I am substituting from here. So, epsilon 1 is equal to U2 by L1 and U2 is equal to P by K1, and that is equal to E1 by L1 into P by K1. K1 being A1 E1 by L1. So, substituting that A1 E1 into L1, striking them off, I get sigma 1 is equal to P by A1. Same way you can substitute it will take 2 minutes, but you can see that sigma 2 is equal to P by A2. Is that clear? So, this particular procedure, which I will summarize in a minute, is in a nutshell what we do in finite element analysis. Now, there are very interesting things we have not talked about. Look at that result. There is always a misconception, mostly among students, that when I have a bar like this with two different E's, E1 and E2, okay, there is always a misconception that when I apply a force to this particular bar, to this bar, for example, what is here, that since E2, say for example, let us assume that E2 is greater than E1, just for an argument. Since E2 is greater than E1, then the students feel that the strains or displacements are lower, strains are lower, and hence stress is lower when I have a higher E2. So, absolutely not correct. Because, why is that? Because ultimately we are looking at equilibrium equations. What does this actually indicate? In one sense, these two come out from the equilibrium of the bar. Okay? Now, sigma 1 A1, if I bring the A1 to the other side, in one sense these two come out from the equilibrium of the bar. Okay? Now, sigma 1 A1, if I bring the A1 to the other side, sigma 1 A1 signifies the internal forces due to stresses. Stresses develop due to internal forces, and in one hand they are nothing but an equilibrium equation. So, the force, whatever be the material, when I apply a force, this force has to be equilibrated by the internal stresses, and when they develop, when these internal stresses develop, they develop in such a fashion that they are independent of E1 and E2. Okay? So, that is a very important thing to realize, because people usually make a mistake, and that is why I have pointed out this particular case. If in fact, now let me summarize it. In fact, if you look at what all the steps we have gone through, we have gone through quite a few steps, though every step was simple, but we have gone through quite a few steps. What is the first step? We looked at the problem and said that this behavior is a simple bar behavior. Okay? We said that this is simple bar. Okay? Please note there is a difference between geometry and its behavior. The same bar, okay, if I apply another type of load, for example, let us assume that this bar has a circular cross section. The same bar, if I apply a load in this direction perpendicular to it, would behave, what would it undergo? It would undergo bending, correct. So, it would undergo bending, and hence the behavior of the body would be like a beam. So, the first thing that we did was to immediately recognize from this problem, and with the engineering knowledge we have the back of our mind, the first thing we said that, look, this behavior is a bar behavior. In fact, I told you that if this is a bar behavior, there is an element called bar element. So, I discretized this using a knowledge of engineering which I had gained, and correspondingly looking at a thing which is close to the engineering behavior in this finite element library. Is that clear? What does it look like, or what is the analogy? You remember that the first day we had a problem of determining the area. When I wanted you to determine the area, what did you do? You said that, look, there is a triangle there. I know what is the area of this triangle. Okay? Immediately you discretized that body into a triangle. Similarly, you know what is the area of a circle, and you apply that knowledge, and that is what you did that day. You applied that knowledge and you knew that there is a circle whose area is known, and so on, right? And this is exactly what you are doing here. Knowing how the material or the geometry is going to behave under a combination of the geometry as well as loading, you said, let us choose bar element, first thing. So, after choosing the element, what did you do? You discretized it. Okay? You divided it into two elements. Why did you do it? Before you did this, you immediately had an idea of what is stiffness of a bar. That is what we did. Okay? What is the stiffness of a bar? Then you realized that there is going to be a term, say A1 E1 by L1, which we called as K1, and A2 E2 by L2. Okay? So, after having realized this, you also felt that if I divide this into two elements, it is nice, because this guy has one area, this guy has another area. So, I can have two elements, so that my calculation of stiffness matrix does not become very messy. Is that clear? So, you chose this element, again looking at geometry and having a knowledge of the stiffness matrix or stiffness determination. So, that is the second step you did, you discretized it. As a third step, what did you do? You wrote down what is the stiffness of each of these elements, right? In that process, you also defined K1 and K2, right? What is the next step you did? you assemble them. You assemble them, right? You put them together so that I get a global stiffness matrix. Okay? So you got what is called as global stiffness matrix. So next is the assembly procedure. After having assembled it, you applied boundary condition. This is a very crucial step in finite element modeling, finite element analysis. Let us take a simple example now apart from this to show the importance of boundary conditions, which not only students but practicing engineers also get confused. The question they ask is, let me keep this figure because we will explain that again. The question they ask is, suppose I have a bar. Let's stick to the bar for the time being, and if I apply a load, say P, on either side of the bar, which is typical, very simple thing. I take this bar, go to some testing machine, and usually this is the type of free body diagram you would usually put. Okay, is that clear? It's a simple thing. So the question that people ask is, now where is the boundary condition here? Can I not solve it straight away? Can I not solve it straight away is the question. The other confusion is that, look, why do you want to apply boundary condition? Because anyway I have u1, u2 and u3 in this previous problem. Similarly, I have u1 and u2 in this problem, and I have 3 equations. So why not I go and solve it? Can I solve this without applying boundary conditions? Because that is what it looks like from the free body diagram. But unfortunately, that's not true. It is just because you have written down 3 equations, and just because you have 3 unknowns, it doesn't mean you can solve this equation, because these equations have to be linearly independent. Then only it would be possible to solve this problem, right? Because you have got this particular equations for the stiffnesses from just the equilibrium, internal equilibrium, right? So in other words, the solution for this problem, as far as, say, for example, displacement is concerned, will not be unique. Physically, what does it mean? It means that I have to get the correct positions of these, for example, ends as I apply this bar, as I apply the load for in this bar. Now, that is not unique. It is something like adding a constant to an integration, right? Something like adding a constant to integration. For example, I take this bar and then determine the stresses for this bar in this position. Okay, I will get a particular u1 and u2, right, with respect to, say, a coordinate system. On the other hand, if I take the same bar here, same bar, and apply the same loads and determine the displacement and stress, it has to be the same. But I would get a different value. This can be, say, at a distance of around 5 units from the origin. This can be at a distance of 3 units from the origin. So you won't get a unique u or unique solution. In other words, a rigid body mode can be applied. There is a rigid body translation, okay, a rigid body translation that is applied here. And these kind of rigid body translations will not affect the result, okay, physically as we see it, but will make it impossible to get a unique solution. So we have to arrest this kind of rigid body motions so that we get a unique solution. Look at that again. Then the question that you may ask is, how do I solve this problem? Okay, this is the free body diagram. I can tell we are all people with mechanics background, so we would like to put the free body diagram and then start this problem. Then how do I solve this problem? Where do I put a boundary condition? Yes, one solution, as you say that immediately, why not I fix it here and then solve this problem? Or these two problems from which I started, are these two problems the same?
So you are like positioning 1 at 0, and like you're fixing 0 and like moving 2 part. Similarly, you can have here fixing 2 and then move it.
Right. So in other words, you feel that both the solutions are the same, right? You are just fixing it, and when I fix it, the reaction is anyway going to be P, that's what you are saying, and hence these two problems are the same. Yes, to a certain extent what you say is right, but a purist will not agree to it for a simple reason that if I take a small element there, okay, in this particular problem, corresponding element being here, in this particular problem, okay, when I fix it, that element won't move. Can you say the same thing of this element? No, this element would start moving. But what you say is right, because the stress anyway will not be affected. Okay, stress would be the same. On one hand, in this problem, if I plot the displacement right across, okay, it would start from 0, right? On the other hand, the displacement here would start from negative, okay, negative value. If I consider this as the negative x1 direction, start from a negative value. So how do you solve this problem? One of the easiest way to solve this problem is to exploit what is called as symmetry of the problem. What is meant by symmetry? Now, let us look at a material particle. Let us sit here in this material particle and see what's going to happen to us as this load is applied. Go and sit at this place. When you sit at this place, this guy here to the left is going to pull me, and this guy to the right is going to pull me. I'm going to have a horrible stress state. Both the guys are going to pull me. They're going to pull me with equal force. What happens? Equal force, both guys are going to pull me. I'm going to stand there. Please note again, when I'm going to stand there doesn't mean that I have no stress. Okay, I am stressed. Both the guys are pulling me. So in other words, all these material particles which are sitting on this line are not going to have any motion, which means that instead of solving this problem, I can say take half of the problem, I can take that problem, fix this side, and then apply a load here, okay, and then solve this particular problem. Okay, we'll come what is the boundary condition, what is the load to be applied, all these things we will come later. Okay, just note that the whole lesson here is not symmetry. Symmetry will come a bit later in the course, but what is important to realize is that we cannot solve a problem without giving boundary condition. That's the lesson I want to look at it from this example. Okay, we will talk about symmetry, which is slightly more complex, later in the course, but note this carefully. So hence boundary conditions are important. Once you apply the boundary conditions, you can solve the problem, determine the displacements. So what is the result you are going to get from finite element? The result that you get from this finite element analysis are displacements. You don't get stress, please note you get displacements. Then you go back and through strain displacement relationship, okay, you find out the strain, and then through stress strain relationship you determine stress. Is that clear? Okay, so this in a nutshell completes all the steps that are required in order to solve this problem. Yeah, any questions?
What happens if bar is inclined?
Yeah, so that's a good question. So what the first thing is, what happens if the bar is inclined? Suppose I want to solve the same problem, this same problem which is sitting here. If I have to solve this same problem with the bar being in an inclined position, okay, or for that matter an element being inclined, how do you solve this problem? Is there going to be any difference in the procedure? Now this problem becomes important because of 2 or 3 reasons, or rather most important reason is this. There are a number of softwares that are used to do finite element analysis. We will again look at where we use softwares, what is that we use as with respect to different steps that we have seen. But they immediately, these softwares have a tendency to give names. Looking at this, they will say 3-dimensional bar element, a generalized bar, 3-dimensional bar element. Okay, this is the name they would give. Okay, 3-dimensional beam, 3-dimensional bar. These are the names that are usually given. Right? Now, people get confused because, as we had just now talked, the bar can take only degree of freedom along its axis, right? So what do you mean by 3D or displacement of a node? There are 3 degrees of freedom for the displacement of the node. That's what they would say. What does it mean? Or how am I suddenly going to get 3 displacements? Does it mean that this bar elements can also take into account bending? No. What essentially it means is that, for example, if this is the original bar, okay, and if this is the displacement, and this displacement happens to be, say, ui, and that displacement happens to be uj, okay, this displacement, what essentially you do as far as the stiffness matrix is concerned is to resolve these displacements along the direction of the beam, or of the bar, okay, and if this happens to be, if this angle happens to be beta, okay, and if let me define C is equal to, say, cos beta, then if this is going to be ui, then this shortening, keeping, say, for example, let's say uj is equal to 0, so that things become easier to understand. Then this shortening of length happens to be what? Cui, okay, and the force that is developed due to the shortening of length now is to be calculated. Okay, let me call this force as F. That will be same as what? AE by L into CUI. So if I call that force as F, let me write it here. F is equal to AE by L into CUI. And this force is now resolved again in the x and y direction, which means that if I call this force that is acting in this direction as, say, Pi, and the force that is acting, say, in this direction as, say, Qi, then Pi is what? Is equal to AE by L into C squared because CUI into C. Okay, so this becomes AE by L into CUI into C. In other words, please remember C is cos beta. Same way you can get Q to be defined as Qi is equal to AE by L Cui into, correct, well, let us call that as sin beta and S. Okay. In other words, it is possible to develop the stiffness matrix of an inclined bar by following the same steps, but by resolving the forces as well as displacement along the axis of the bar. So my physical behavior of the bar does not change, but I change a little the mathematics that is involved, so that I am able to define a more general inclined bar. So the first column of the stiffness matrix would now look like the corresponding stiffness matrix would look like C squared Cs minus C squared minus Cs. Is that clear? Corresponding to 4 degrees of freedom. Please note now that we call this as 4 degrees of freedom, 2 in the x and the y direction for this node and 2 in the x and y direction for this node, though physically in actuality the bar only shortens or lengthens. So this displacement along the axis of the bar has been resolved, and that is what you get. Okay, so the stiffness matrix now becomes 4 by 4. So the K is now, so which would result in, this would result in K, which is a 4 by 4 matrix. Okay, so that's clear. Fine. Now, is there any other question?
What about the 3D?
Yeah, right. See, one, that's a good question. Again, we have to discuss that point. And let me repeat that question, what he says in a minute. The problem which we have done so far involves only a uniaxial problem. In other words, uniaxial stress. Now, there are a lot of things which we have to change in the way we are going to think further. What is it that we are going to change, or why we should change our thinking? Now, in the uniaxial problem, we did not have much difficulty in understanding stress, because stress, we said, is just E into epsilon, finished it. There is only one stress called sigma, and it happens to be, or it turns out to be, the same as load per unit area, P by A1, P by A2, and so on. Okay? So there are two very simple definitions we used. One is to define strain, just change in length by original length. Okay? The other one which we used was just E into epsilon, which turns out to be P by A. What happens to the complex situation? Many of the examples which we saw the other day are definitely not in the class of example which we have seen. Or in other words, none of them are one-dimensional bar type of elements. All of them were 3D. Remember the railway wheel which we saw? It was a 3D problem. Okay? Now, in a 3-dimensional case, where the deformation is not also homogeneous, in the sense that the stress, as you had seen, varies from one point to the another point, how do you define stress? Now, load per unit area, or P by A, becomes quite difficult to define. What is P by A? Okay? Now, what is that area that we have to take? Pardon? Can you take projected area? See, the problem here is, suppose I have a sheet, okay, with a hole and so on, and I start applying loads, what we call as biaxial loads, like this and say like this, okay, and so on, then we know that the stresses near the hole may be different from the other region. Okay, there can be one hole, or there can be a circular hole or elliptic hole or whatever it is. They are going to be different from other positions. Okay. Now, in other words, you probably you all studied that there is stress concentration region near this hole. Probably all of you would say. Okay, a very simple answer you would give. What do you mean by stress concentration region? You would immediately say that, look, when there is a hole in this part, then the stresses near this hole is going to be high, correct? It's going to be high. Now, what is this stress? Is it just P by, say, suppose I say this is say P2 and this is say P1. The question that comes to our mind is, how do I now define stress in this part? What is A now? P2 by what A? If you say it is projected area, that's what many people say, and so the stresses is P2 by A, then you mean to say that at all these regions the stresses would be higher? Then it becomes a problem, because immediately you would again come and tell me that no, it is not like that, very near the ends the stresses would be higher. In fact, when the hole is very sharp, stresses may even reach infinity. Okay, there's a singular point and so on. Let's not worry about those things now, but it's important to realize that now the stresses would change as I move away from this corner. If I use one area, as you said, if I use just the projected area, the normal area, then I would get only one answer, right? For example, in a more complex case of the railway wheel, or for that matter the connecting rod or the tire and so on, stresses varied from point to point, okay, from one position to another position. Then what is the area that I am going to define there, if it is just load per unit area, right? Is that clear? So we have to put stress in a much more proper perspective. Okay, and what is it that we are going to do for that? We are going to define what is called as state of stress at a point ultimately. But before we go to the state of stress at a point, we have to define first of all what is stress in a much more rigorous fashion than just load per unit area, right? Let us say, see, in your earlier classes you would have used coordinate systems. Usually you will call this as x, y, z or z. Okay, Americans call z as z. You know why? Because in English z is never defined or never pronounced as z. Take for example, z is used in zebra, but you have z to be, okay, the phonetics is z to be z. So the Americans define x, y, z, right? But we are not going to get into even that complications in language. We are going to define, for example, these coordinate systems to be x1, x2 and x3. Okay, let us now take a complicated body. Okay, and then let us say that I apply loads on the body and I have some boundary conditions. Now, before we go further, let us look at the type of loads that happen to be present in engineering components. The loads obviously are due to certain external influence. Is that right? The loads are due to external influence. Now, what are the types of external influence? Can you classify them? Yes, you can classify them into two categories. One which produces what are called as body forces, and the other which produces what are called as surface forces. Now, what are body forces and what are surface forces? There are external influences like gravity or centrifugal force, which happens to be present in the in the total volume of the body. Though they are external influences, they are present in the volume elements of the body. Their influence is ever pervading throughout the volume of the body. Such forces which acts on the volume of the body are called as body forces. On the other hand, we have what are called as surface forces. The surface forces, for example, contact forces. You have a connecting rod, there is a gudgeon pin which is in contact in one end called small end and the crankshaft the other end, and so on. So, there are contact forces. So, these contact forces, as an example, gives rise to surface forces. Or when a body is in water, okay, there is a force that acts on the surface, and so on. See, so the forces that act on the body can be classified into body forces and surface forces. Now, there can be a question. Usually, in all our earlier classes, I have applied force something like this. I have put an arrow and said that, look, this is a force. And probably many of you would have called this force as a concentrated force. Now, where do I fit in this category? Where do I fit in this concentrated forces? Is it body force? Surface forces, correct. So, these forces are surface forces. In actuality, there is no such thing as a concentrated force. Forces do not act just at one point. Okay? They act in a very, very, very small area, infinitesimal area, whatever it is, it acts on an area, right? And that has been modified, okay, to be a concentrated force for engineering purposes, and hence we have this term concentrated loads or concentrated force, and that happens to be a part of the surface force. So, stresses are produced due to this kind of forces, right? Then what is a stress? How do you define a stress? Now, first thing that you have to realize is that stress is defined, say, at a point, say P. Stress is defined at a point P. How is it defined at a point P? We will come back to our original definition, but before that, what we have to do is to imagine that the body can be split. I am not going to, please note that when I cut the body, before I go further, you should realize that when I cut the body, it does not mean that I am taking an axe or something and cutting the body, and what about all the damage you are going to do to the body. No, we are just imagining. Okay? Now, so the first thing is that the stress can be defined at any point P of the body. In order to determine the stress P, okay, I have to cut the body by an imaginary plane. I will say that, oh, you want the stress at P, so let me cut it by an imaginary plane, okay, and then take, say, a part of the body out. Let me take the body, part of the body out, right? You want me to concentrate on P? Yes, let me concentrate on P. This is the point P. Okay? So, the next thing I will do is, now what is the influence of the other body or the other part of the body which you have cut onto the body which you are now having in your hand and looking at it. Please note the body still has all the forces that are acting. It's not that I've removed everything and cut the body, but I've just cut the body, taken it imaginarily and looking at this point P. We will go through that in the next class to define what is stress from this point of view, okay, in the next class. But before that, if there are any questions, I'll answer. Yeah.
So this concept of stiffness matrix is true only for the bars of constant cross-sectional area.
Yeah, very good. So that's the next question. That's a very important question. It's good that we stopped here and you asked the question. The technique that we used in order to arrive at the stiffness matrix is a direct method. So the question is that, is this the only way, or in other words, if I have a tapered bar, if I have some other shape and if not going to be bar but any other shape, how do I determine stiffness matrix? Can I use this kind of same approach? The approach that we used is what is called as a direct method. But this direct method may not work for all cases. But we have to resort to other engineering principles. It may be, okay, based on energy theorems. It may be based on virtual work principle and so on. So we are going to answer that question later in the course. But in order to do that, we have to first understand stress, and hence we are now going to look at stress very closely. Once we do that and we understand what is stress, what is strain in a much more general setting, okay, then it would be possible for us to go into more involved theorems, define them clearly, and then define stiffness matrices, right?